Hello everyone, this is Dr. Ashok Kumar from Government Women Engineering College Ajmer. This is lecture 2 on wave propagation series, and in this lecture 2 we are going to discuss about tropospheric wave propagation. Sometimes it is called as a space wave propagation. The following contents will be addressed during lecture 2 of this wave propagation series, and in this lecture 2 we are going to discuss about the field strengths due to the space wave, then tropospheric wave propagation, tropospheric duct wave propagation, line of sight propagation, tropospheric scattered, and some problem based on the tropospheric wave propagation. The contents of this lecture 2 of this series is prepared with the help of this reference book. As we have discussed that the electromagnetic wave travel from transmitter to receiver or propagate from transmitter to receiver in the earth atmosphere, it is called as a space wave or tropospheric wave propagation. The field strength at the receiver in space wave propagation is contributed or dominated mainly the ground reflected wave and direct wave, as we have discussed about the ground reflected wave and direct wave in lecture 1 of this wave propagation series, and this is occur in the tropospheric region, so we are saying it's a tropospheric wave propagation, or sometimes it is called as a space wave propagation. The space wave field strength is affected by the following parameters that we will discuss in this lecture. The curvature of the earth imperfectness and roughness, hills, stalls, building and other obstacles, height above the earth, effect of the polarization, in which some parameters that we have discussed in lecture 1 of this series, and we are going to discuss about mainly the atmospheric effect of space tropospheric wave propagation, and this propagation is generally used about 30 megahertz, and it is used for FM, TV, radar application, and it is also used in high frequency, very high frequency and ultra high frequency bands. So first we have to calculate about the field strength due to the space wave or tropospheric wave propagation. Sometimes it is also called as a ground wave propagation, and ground wave propagation is the combination of surface wave as well as the space wave propagation. So we can calculate or we can derive the expression for electric field strength, and you can consider any antenna book in which you can find out the derivation of this electric field strength. But here we are considering only the equation, that is E equal to twice E naught by D sine 2 pi HT upon lambda D. And here you can see that this is the direct wave that travel the wave from point P to Q by using direct path, and another is the ground reflected path. Here you can see the first the wave travel from point P to point X, then point X to the point Q, and in this case we have considered the earth is a flat earth. We cannot consider the curvature of the earth for calculation of the field strength in a space wave. So we have considered the flat earth, then we can calculate this expression, or we can also return this expression in terms of uh, electric field, and that is 4 pi STHR upon lambda d square in E naught. Here we can say that sine of theta equal to theta. We can consider, then we can calculate this another expression. Here E naught is the field strength due to the direct ray at a unit distance. So we can say this is the direct ray that travel, and it is the initial field strength. St is the height of the transmitting antenna. Here you can see from the surface of the earth. Hr is the height of the receiving antenna from the surface of the earth, and d is the distance between the transmitter and receiving antenna. Here you can see. So by using the image principle theory, we can derive the expression, and the derived expression is given in equation 3. Here the another important parameter is the E naught, and this E naught is the field distance due to the direct ray at a unit distance, that we can calculate E naught is equal to 300 root of P in terms of kilowatt divided by D in terms of kilometer. Here D in terms of km is the kilometer. So we can find out the field distance, and this field distance is affected by the following parameters as we have discussed in this slide. Further, we are going to discuss about tropospheric wave propagation, and in the troposphere, the relative dielectric constant is slightly higher than the unity due to the presence of atmospheric conditions, and in particular the water vapor. In that case, the relative dielectric constant, I mean epsilon, are having slightly more than the 1. So in a tropospheric region, the surface of the earth to a height of about 6 km at the poles and 18 km at the equator is considered to define the tropospheric region. The relative dielectric constant, I mean epsilon r, is the function of temperature, pressure and humidity or water vapor pressure. The typical value of epsilon r of the surface of the earth is found to be 1.000579, and you can see the more detailed analysis about this typical value in the book of Griffiths 1987. The value decreases as the function of the height above the surface of the earth increases. In that case, we can calculate the velocity of electromagnetic waves in a medium depends on the dielectric constant of the medium, that we have calculated by using this expression 4. V is equal to C upon root of epsilon r, which is equal to C by n. So here you can see the propagating velocity is depends on the dielectric constant of the medium. In that case, we can calculate, or we can also represent n equal to root of epsilon r, and it is called as a refractive index of a medium. N is the refractive index and epsilon is the dielectric constant, and c is the velocity in a vacuum. So at the surface of the earth, mean sea level, the refractive index of the air is 1.000289. Therefore, it is a common practice to work with a parameter known as the refractivity. So we are considering the refractivity parameter n by considering the refractive index of the air, that is this value. So the refractivity is related to the refractive index by using the expression 5, and here you can see capital of N is represented the refractivity, which is equal to n minus 1 into 10 to the power 6. So at the surface of the earth, the refractivity is equal to 289. So by using the equation 5, we can calculate the refractivity at the surface of the earth, which is equal to 289. For a standard atmospheric condition, the refractivity falls off linearly up to a height of 2 km above the surface of the earth, and can be expressed by using this expression or equation 6, and which is equal to n is equal to 289 minus 39 h. So here you can see this is the refractivity at the surface of the earth minus 39 h. Height is the height from the surface of the earth, and it is known as the standard atmosphere or normal atmosphere. If the refractive index of the standard atmosphere, that we have represented in terms of expression 7, and the refractive index also very close to the unity, so radius of the curvature reduces. So we can say r is the curvature radius, that equal to 1 upon 1 minus dn by dh. So this can be calculated from the equation 7 by differentiating, then and putting the value of dn by dh from the equation 5. This is the equation 5, and we have calculated dn by dh, so we have differentiate with respect to the height, and that through which we can calculate the refractivity gradients and dn by dh, and the radius of curvature in terms of refractivity gradient equal to r equal to 10 to the power 6 upon minus dn upon dh. So this equation is 9 is very important that we are considering to understand the different types of wave propagation in a tropospheric region. If the ray is propagating in a standard atmosphere as described by the refractivity profile, here you can see the figure, the wave propagating through a standard medium above the spherical surface. In that case, here this is the spherical surface, and in this is the transmitter, and here you can see somewhere at the receiver the wave generated from the transmitter it travel in a tropospheric region. In that case, if the gradient profile dn by dh having the value of minus 39 per kilometer, then we can say that this is the condition of standard atmosphere, and we can calculate the radius of the curvature of the ray path by putting the value of dn by dh equal to minus 39 per kilometer in equation 9. Then we can get the value of radius of curvature of ray path, which is equal to 25641 kilometer. So we can say the ray drops towards the surface of the earth at if the radius of the curvature equal to 25641. Another condition that we can consider dn by dh is equal to 0 and dn by dh is equal to minus 157 per kilometer, and dn by dh if less than minus 157 by per kilometer. In that case, we can define the different types of propagation, and if the value lies between 0 to minus 39, it is called sub-refraction. If minus 39 to minus 157 per kilometer, then it is called as a super refraction, and this is if the value of dn by dh less than minus 157 per kilometer, then it is called as a duct propagation that we have discussed in subsequent slide of this lecture. If the diffractivity change dn by ds, then the ray wave does not undergo refraction, and hence it is follow a straight line path. So we can say this is the line dn by ds, so it follow the straight path. If the refractivity gradient between, as we have discussed, 0 to minus 39 by per kilometer, in that case the electromagnetic waves is lower than the standard atmosphere, and it is known as a sub-refraction. If the refractivity slope is greater dn by dn less than minus 39, then the wave is refracted more than in a standard atmosphere, and it is called as a super refraction. Here you can see if the value of dn by dh is equal to minus 157 per kilometer, then we can calculate the radius of the curvature of the ray, that is calculated by using expression 11a, and this is equal to 6370 kilometer. So it is also called as the radius of the earth. So we can say that the radius of the earth are equal to 6370 kilometer, then this type of propagation, duct propagation, will be occur, and a horizontally incident wave travel parallel to the surface of the earth. Here you can see, and this wave is travel according to surface of the earth. If dn by dn less than 150, the radius of the curvature of the ray is smaller than the radius of the earth, so the ray can therefore follow the surface of the earth and get reflected from the surface. Here you can see, uh, this is, and it is called as a tropospheric duct propagation. And in figure 5 you can see the different region of super refraction, sub-refraction, and duct propagation on a NH plot. Here you can see this is the N and this is the H in terms of kilometer, and at the different atmospheric condition, here you can see if dn by dh is equal to 0, then there is no refraction. If dn by dh is equal to minus 39 per kilometer and lies between 0 to 39, that's sub-refraction, and this is the super refraction, and this is the ducting occur when dn by dh is equal to minus 150 per kilometer. And according to this graph, we can also understand the regions of refraction, sub-refraction, and duct propagation. Then further we are going to discuss about line of sight propagation. Over a spherical earth, the surface, the maximum possible direct wave communication distance depends on the height of the transmitting antenna and height of the receiving antenna, and as well as the atmospheric condition. For propagation calculation, as the mean value of R naught, that value we have calculated equal to 6370 kilometer. As here you can see, when the dn by gradient value, dn by ds equal to minus 157 per kilometer, it means we are considering the case of underducting. In that case, the radio wave travel, we can calculate the line of sight propagation. If the dn by ds, the radio wave travel along the straight line, therefore the maximum range is contained when the straight line join the two antenna graze the surface of the earth. Here you can see the figure 6. So this is the case we are considering, and by using or by analyzing this figure 6, we can calculate the line of sight distance, and this we have calculated using this analysis. First we are considering the triangle AOC. Here you can see A, and this is the O is the origin and C is the center point, and we can see that R naught plus ST square is equal to R1 square plus R naught square by using simple geometry. So here you can see we can get the value of R1 square if we are considering the condition R naught greater than HT, then it is equal to R1 square nearly equal to 2 R naught HT. Similarly, from the triangle BOC, we can calculate the value of R2, which is equal to R2 square equal to 2 R naught HR. So by considering the expression of 13 and 14, we can calculate the line of sight distance between the transmit and receiving antennas, and that is equal to, using this expression, which is equal to root of twice R naught, uh, root of HT plus H of R. So here you can consider the value of HT, HR and R naught in terms of SI units, then we can calculate the line of sight distance by using this expression. Further, we are considering the case when the propagation of the radio waves under standard atmospheric condition, as we have discussed here, minus 39 per kilometer. It means this is the condition of standard atmosphere. If it is in the under atmospheric condition, then we can calculate the equivalent earth radius, and this equivalent earth radius we have calculate by using this expression 16, 1 by r is equal to 1 by r naught minus 1 by r, and multiplying the both side by r naught and rearranging the equation 16 after multiplying, then we can get the value of re by r naught, which is equal to 1 upon 1 minus r naught by r. So by substituting the value of actual earth radius 6370 kilometer and r is the effective, that is equal to 25641. In that case we can calculate the equivalent radius, which is equal to r equal to 4 by 3 r naught. So we can say the ray path can now taken as a straight line and the earth having a radius 4 by 3 r naught. In that case the ray path can travel in a straight line. The standard atmosphere is valid up to a height of 2 km from the surface of the earth. So this is another important expression. If the curvature of the earth is considered, in that case we can also calculate the distance between the line of sight uh, distance that we have given or represented in expression 15 by putting r not equal to ra, and we are considering 4 by 3 r naught, then we can calculate it. Then further we are going to discuss about how the tropospheric scattered region is occur. So the tropospheric scattering phenomena can be establish a communication link over the distance much beyond the radio origin. As we have discussed, when this condition is above this condition or beyond this condition, in that case the radio origin, the tropospheric can scatter electromagnetic waves due to its inhomogeneous nature. The tropospheric scattering has been attributed to the blobs of the radio refractive index changes and turbulences. These could be due to the sudden changes in the temperature as well as humidity or the presence of the dust particles. So, if this type of situation beyond the radio origin occurs, in that case, tropospheric scattered is occurring, and here you can see this is the surface of the earth, and this is the tropospheric communication link. This is transmitting antenna, this is receiving antenna. Here you can see, and this is the region is called as the scattering volume, and this is the angle that we can call is a grazing angle. So we can say that the tropospheric link consists of the transmitter, the main beam of which can view angles with the horizontal less than 4 degrees. So scattering volume is a common volume shared by the two beams. Here you can see this is the first beam and this is the second beam, and similarly here, sorry, this is the first beam and this is the second beam. So by using these two beams, the common shared volume is called as a scattering volume, and here you can see this is the scattering volume, and it is just a few kilometers on the surface of the earth. Due to the presence of more than one path through which the signal from the transmitter to reach receiver, or we can say it's a multi path environment exists between transmitter and receiver. In that case, the signal travel from the transmitter will reach receiver with different time delays. In that case, the fading is occur. So, in a tropospheric link, the fading is also occur due to the multipath environment. Further, the tropospheric can also establish communication link in ultra high frequency and microwave frequency band. These links typically have a range of up to 1000 kilometers and have bandwidth of few megahertz. Tropospheric links can be used in multi-channel telephone and television application. So we have discussed in this lecture about the tropospheric wave propagation. In this lecture, first we have discussed about the electric field that we have discussed. Then further, what parameters are affected the electric field intensity. Then further we have discussed about the different atmospheric condition, and in that case we have discussed about the tropospheric wave propagation mechanism in atmospheric conditions. Then further line of sight communication, and we have calculated due to the presence of uh, curvature of the earth or in the presence of flat earth, and through which we can calculate the distance between the transmitter and receiver. So and finally the tropospheric scattered is discussed in this lecture. Further, we are taking one problem that is based on the based on the theory that we have discussed in this lecture, and the parameters are given f, r naught, and r is given, and the transmitting antenna height is also given. We need to calculate the height of the receiving antenna. So by using this expression as we have discussed in equation 15, and we can calculate the value of receiving antenna, and this value of receiving minimum height of the receiver antenna h of r equal to 82.2 meter. These two problems are given here to test yourself, and these two problems again based on the line of sight path or line of sight communication. In that case, you can calculate the effective earth radius, and in problem 3 you need to calculate the field strength at the receiving end, that as we have discussed the field electric field intensity in a space wave propagation or due to the space wave. By using that equation you can consider or you can solve this problem 3. So problem 2 and 3 are given here to test yourself. Thank you very much for watching this lecture. I hope this lecture is beneficial for you. In the subsequent lecture of this series, we are going to discuss about ionospheric wave propagation.